Sir, I hope my voice is audible.
Yes, your voice is audible to me. Am I clear? Am I audible to you?
Yes, sir. Yes.
Yeah. So,
So,
Dr. Prantik, are you available?
yeah. So now we'll proceed towards our next session, which is the industry session. We are delighted to have Dr. Prantik Chatterjee for our industry session. I would like to present a brief introduction about Dr. Prantik Chatterjee. Prantik Chatterjee is a senior software engineer in the Simulink Design Verifier team at MathWorks. He completed his PhD in computer science and engineering from IIT Kanpur in 2023. During his PhD, he worked in collaboration with Microsoft Research to develop efficient techniques for verification and testing of software using proofs of satisfiability and multiverse analysis. He was awarded the Intel India Research Fellowship in 2022 for his contribution in the domain of formal property verification. His current research interest lies in the cross-disciplinary domain of formal methods and machine learning. I request Dr. Prantik Chatterjee to share some ideas regarding the role of AI or ML in software development and sustainability.
Hi everyone. Good afternoon. Am I audible to everyone? Can you please let me know?
Yes.
Uh, yes, sir.
Yes, sir.
All right. Can you also see my screen?
Yes, sir.
Yes, sir.
All right. Thank you. Okay. So again, hello everyone. Good afternoon. So I am Prantik, and I'll be presenting this talk on AI ML in software development. So the purpose of my today's talk is to briefly introduce you guys to the kind of AI ML techniques that are being used in the domain of software development. And I'll be focusing on a very short representative techniques, tools and techniques, and I'll be giving you a brief overview using very simple examples. Okay, so moving on. So more than half of the software development life cycle we spend on actually discovering and identifying program bugs. Now the question is, why should we care about program bugs at all? So if you look at recent reports, you will see that an estimated 620 million developer hours a year are spent on debugging software failures, and this is at a cost of roughly 61 billion US dollars. So obviously, this is a very costly procedure, discovering and debugging softwares. Now, what happens if we do not properly debug softwares? So a very prominent example, in 1962, US launched this Mariner 1 space probe. But unfortunately, this space probe had to be self-destroyed after only about 290 seconds after launch, because there was a bug in the software which was driving this probe. So the bug was very simple. There was one extra hyphen in the code, which resulted in this probe being feared. So the directions that were being provided to the probe were buggy, and eventually it had to be self-destroyed. So you can understand how even a very simple bug can cause a very costly mistake. So the cost of this failure at that time was 18 million. In today's terms, it will be around 169 million US dollars. In another more recent example, in 2012, there was a company called Knights Capital Group. It was the largest trader in US securities at that time, and it had a market share of around 17% on the New York Stock Exchange. So in their recently developed software, they had a piece of code which was protected by a flag. Unfortunately, it was untested code, and for some reason, the code was activated because it was not properly tested, and there was a bug. The flag got activated. The flag activated this buggy piece of code, and it resulted in a loss of 440 million US dollars in just 30 minutes. And this Knight Capital Group eventually went bankrupt. So these examples clearly shows you that we should actually care about program bugs, because even the smallest mistakes can cause largest impacts. So we have established that bug detection is important. Bug detection or software debugging is important. But why is this a challenging problem? So this is a challenging problem because you know that as time has progressed, as we have developed more and more softwares, the size of the softwares and their complexity have continued to grow. So the companies that develop these softwares continue adding features to them, and eventually it has resulted in these pieces of softwares which may contain millions of lines of code with tens of thousands of procedures calls. Now, if I write a simple program, let's say I want to write a program which takes an input and tries to say whether this input is even or odd. So this is very simple, right? I can just hand test this code. But if you try to manually debug these programs or softwares containing millions of lines of codes, it's simply next to impossible. So eventually, these research community had moved on to automated testing and automated verification tools where try to automatically detect these software bugs. But even after decades of research, automated techniques still do not scale well or are not precise enough on these real world softwares. Because as you continue to improve your bug detection or debugging techniques, the complexity of software also continues to grow. So eventually, you have to. Yes, is there a question? All right, so I'll continue. Okay, so as the complexity of software continues to grow, so we'll have to invest more and more effort into these automated software debugging techniques. Now, there are two very distinct techniques in software debugging. One is called verification, another is called testing. Verification tries to answer the question whether a program violates the required property. So what can be properties? For instance, property could be division by zero, or it could be null pointer dereferencing, things like that. Now, the way verification works is that it is an exhaustive strategy. And verification tries to say whether the program can violate this required property or not. Now, verification is known to be sound and complete. Sound because if you have a verifier, and if it says that a program contains a bug, then that program actually contains that bug. So it will be a true bug. And it is complete because the verifier is mathematically guaranteed to give you all the bugs. So essentially, if a verifier says that a program does not contain a bug, here by bug I mean this property. So let's say a verifier says that this program, in this program, a division by zero cannot occur. So that means the verifier has computed a mathematical proof which shows that this required property violation cannot occur. So therefore, verification is sound and complete, and it can prove the absence of property violation bugs. Now the problem is it's a very important technique, but the problem is it requires an analysis of the source code of the program. And the way verification works is that it relies on something called an SMT solver. So essentially in this technique, you will try to convert your program into first order logic theorems. You will provide this theorem to a SMT solver, and the SMT solver will try to say whether this formula is satisfiable or unsatisfiable. Now, as you can understand, this is an undecidable problem, and therefore it is not guaranteed to terminate. So you can actually prove the absence of bugs, but your approach is not guaranteed to terminate. So that's why it is very difficult. I'll not say very difficult, but it is somewhat difficult to apply verification in practice. Now, in contrast, you have these testing strategies. Now, testing strategies are sound but not complete. So essentially, this means that a testing strategy can say that there is a bug in a program. It can try to find a bug in a program, and if it finds such bugs, then the bug also actually exists in the program. But if a testing strategy does not find a bug in the program, that does not mean the program is correct. It can happen that the program is buggy, but the testing strategy simply did not catch the bug. So essentially, in testing, we are trying to answer this question whether a program produces the expected output for a given input. So these, obviously, as you can understand, these requires the program to be executed, but the analysis of the source code of the program is not a necessity, which is important because let's say you have some proprietary software and you don't want to expose the source code of the program. So you can simply you can simply hand over the testing of your program to a third party, and they can, even without looking at the source code of the program, they can try to come up with test cases. But the problem, as I have said, it is that testing strategies cannot prove the absence of bugs. But on the other hand, it is very fast and scales well to large real-life softwares. Now, as there are different directions, as we have seen with verification testing, there are also two very distinct approaches. So these two approaches are, first one of them is these formal method-based approaches. The formal method-based approaches mostly work with these SMT solvers, like the example that I gave you earlier. Now, examples of these formal method-based approaches is verification with bounded model checking. So in bounded model checking, essentially, given a program, you will try to convert it to a bounded logical formula. So bounded means your program can have these recursive calls and loops, right? Now, you have so while doing this bounded model checking, you assume that your program can only call certain recursive procedures onto a user-defined depth of D. And loops can also be unrolled onto a certain user-defined depth of D. So that becomes your bounded model checking problem, which is much easier than the unbounded model checking, where you can assume that recursive procedures or loops can go up to any depth. Now, this is also a very popular approach. In fact, Microsoft extensively applies this method to detect bugs within Windows device drivers. And then you have another formal method-based approach, which is testing with concolic execution. So it is also another formal method-based approach, and it is widely used by uh, a lot of companies. In fact, MathWorks uses this to. So the way we use this approach in the Simulink design verification team is that there are these companies which designs engines, right? So for instance, you have Toyota, Nissan, and Boeing. All of these companies design engines, but while designing these engines, they actually use this product called Simulink, where you can actually, rather than going to the physical design, you can do an initial mathematical design. And on this mathematical design, you can do reasoning to find out whether these design contains any errors or not. So MathWorks allows you to do this concolic execution on these designs to find out bugs. So this is essentially testing with concolic execution. And on the contrary, you have these AI or ML-based techniques. So one example of these AI ML-based techniques is called a fuzzer. Fuzzers are also very extensively used by mostly all software-based companies. For example, Google uses this fuzzer called LeafFuzz. And they have, in fact, like they have extensively used these to generate test cases and detect errors in Google Chrome. So as per their report, they had caught around 25,000 bugs in Google Chrome using these fuzzing techniques. And then there is another application which is called fault localization with these spectrum-based fault localization approaches, or SBFL. So the way it would work is that given a program, if it is a buggy program, you would like to identify where in that program the bug lies, in which component, in which line, or in which function there is a bug. So as you can understand, this is finding out bugs, exactly which line contains the bugs. It is essentially a finding a needle within a haystack problem. So it's difficult, but you can automatically do this using this SBFL approach. So in this talk, I'll be mostly focusing on these AI ML based techniques, which is this fuzzing and SBFL. All right, so moving on, let me define a few terminologies that I'll be using through the rest of the talk. So firstly, when I talk about tests or test cases, what are these? So tests are essentially inputs to a program. So when I write a program, let's say again, so taking a very simple example, I have a program which takes an input and tries to determine whether this input is even or odd. So when I have written this program to see whether this program produces these expected outputs or not, I try to run this program with different inputs. So this essentially becomes my test cases for this particular program. And then you have test suits. Test suits are nothing but these sets of test cases. So rather than exercising the program with a single test, because a single test does not capture all the behaviors of the program, you will have a set of test cases with which you expect to exercise or observe most of the behaviors of the program. Now, there is another term which is coverage, which is used within the testing community. So coverage is essentially when you run a program with a given test or a given inputs or a set of inputs, what components of the program gets exercised. So by components, so programs can be tested at different granularities. For instance, one granularity could be the lines of code. In that case, what you will have is a line coverage. So let's say your program has 1,000 lines of code. So using your test cases, what percentage of these lines were you able to execute? So that is your line coverage. Then you can have basic block coverage. Basic blocks are essentially subregions within the program with a single entry and a single exit point. Then you can have branch coverages. Branches are essentially these conditions, if-else conditions. So how many of these branches were you able to take or were you not able to take? And then you have function coverage. Function coverage are these, if you have multiple functions in the program, how many were you able to invoke with your test cases, things like that. And then you have program coverage pattern. So when you exercise a program with some test cases, what kind of coverage patterns you can give? So one of the most popular ones is called a heat pattern. So heat pattern says that given a test case, which components of the program were executed and which components of the program were not executed. So it's a simple 1-0 vector. So let's say in this 1-0 vector, you see the first cell is 1. So that means if you, let's say you have taken one test case and your first component was executed, second component was not executed, and so on. The last component was executed. So this is a simple hit and miss pattern. Then you can have these count patterns. Count patterns are, rather than simply saying hit or miss, you will say that given a test case, how many times were a component executed or not executed. So for instance, in this case, the first component was executed 17 times, the second component was executed 30 times, and so on. And the last one is called a bucket or bin pattern. So rather than simply counting how many times a component was hit or not hit, you divide these number of hits, or rather than counting them, you divide them into buckets. So you can say that if the component was hit from 0 to 10 times, it will be 1. If it was hit 10 to 20 times, then it falls within the second bucket. If the second component was hit between 40 to 50 times, it falls in the fifth bucket, and so on. So this first pattern is used by a very popular fuzzer called EvoSuit. The third pattern is used by AFL. AFL is used by Google. All right. So with the terminologies cleared, let's move on to these how the fuzzers work. So this is a coverage guided fuzzing technique. So what is the objective is that given a program, we want to generate test cases which can test the program. That is all. And it is coverage guided. So essentially, we want to generate the inputs in such a way such that we can observe almost all the behaviors of the program, or at least that is the goal. So why is this important? So as I said, like in MathWorks, we use this product called Simulink, right? And these companies which designs engines, they initially design these engines using these mathematical graphical user interface. So once they have completed their design, they try to test this design to see whether all components of this engine they are exercised or not. So the objective is twofold. So first, they can confirm that there are no redundant components to this design. So if you have an engine, all of its components are exercised some way or other. And the second thing is, since you have observed all the behaviors of the engine. If there is a fault within the engine, you will be able to discover. So essentially, this is the idea behind coverage guided fuzzing. So with fuzzing, we want to generate a set of test cases which will maximize coverage of the program. So our observed behaviors of the program. So the way you start is initially, so it's basically very simple. It's an evolutionary search. I think most of you will be familiar with this evolutionary search. So, but still, let me give you the brief overview anyway. So essentially, you will seed an initial population with a bunch of random test suits. So the random test suits are, let's say your program takes as input an integer, right? So then you can generate a random set of integers and they will become your first generation of test suits. So once you have seeded these with these random test suits, then from these you can select your top K good test suits. So your top K good test suit which provides a maximum amount of coverage. So with this, you will start your fuzzing process. Now, once you have your selection of elite test suits, you can choose a couple of them. Let's say you choose two parents, P1 and P2. Now, P1 and P2, they can be test suits or they can be test cases. Either of them will be fine. So different methods are used by different types of fuzzers. For this presentation, let's assume these are test suits. So P1 contains a bunch of test cases. P2 also contains a bunch of test cases. So once you have P1 and P2, so you set a crossover probability. Let's say this is alpha. So parts of P1 and parts of P2, you take and you concatenate them to form the first child. And the part that you take from each of these parents are decided by this crossover probability alpha. Similarly, the remaining parts of P1 and P2 are concatenated to form the second child O2. So once this crossover operation is done, then you can have a mutation operation. So from these two childs, O1 and O2, you can mutate a few of these test cases, or you can even choose to forego the mutation operations. But anyway, once you have these two children test suits, let's say O1 and O2, now you want to check whether these children are better than the parents or not. If the children are better than the parents, then they are fed back into the initial population. And if the children are not better, then the parents are merged back into the initial population. And this process continues until you have exceeded a given time budget. Let's look at a more concrete example. So let's say from my initial population, I had these two test suits. So P1 and P2. Note that P1 contains two test cases. This is the first row contains the first test case. Second row contains the second test case. And the test cases, as I've said, the test cases are inputs. What I represent here is the given this particular input, what will be the coverage pattern of the program. So assume my program had 6 components. It can be 6 functions or it can be 6 if-else branches. So given the first test case, as you can see, in this, if you execute this particular input on the program, the first component is executed and none of the other components are executed. So this is the coverage pattern given by the first test case. And the second test case or the second input gives you this coverage pattern. So the third component is executed and the fourth component is executed and nothing else. So in this case, if you want to measure your, let's say, branch coverage, if we talk about programs in terms of branch granularity, then your coverage is 3/6 because there are 6 branches, and with these two inputs, you were able to exercise 3 of these branches. So coverage is 3 out of 6. Similarly, if you look at the second test case, second test suit, the second test suit contains 4 of these test cases. And you can see the coverage patterns. Again, the coverage here is 3/6, as you are able to exercise the first component in the second and third test cases, the second component in the first, third, and fourth test cases, and the fourth component in the second and fourth test cases. So both of your parents give a coverage of 3/6. Now, if you want to do a crossover operation, let's say my crossover probability is 0.5. So half of both of these test suits combine to form your new test suits. So you take the first row from the first parent and the last couple of rows from the second parent. You concatenate them. You concatenate all 3 of these inputs. Now you have a new test suite, new children test suite. In the new children test suite, you see that the first one gives you a coverage of 3 by 6. And if you combine the rest to form the second children, it gives you a coverage of 4 by 6 now. So as you can see, the first, second, third, and fourth component were executed by the second children. Now you can go on to perform a mutation on the inputs. Let's say you mutated the input in such a way that these fifth component were not executed earlier, but after mutating the input, the fifth component is now executed. So the coverage of the first children increases to 4 by 6. How do you do a mutation operation? So there are several mutation operations. You can choose among one or multiple of them. It can be like bit flipping, or you can insert certain bytes, you can delete certain bytes, things like that. Now, the second test suite, you can also choose to mutate. Assume that after mutating the second input, now the coverage again increases in the second test case. So now your first children gives a coverage of 4 by 6, and your second children gives you a coverage of 5 by 6. So now you want to determine whether your couple of parents are better than this couple of children. So the way you will do it is you try to determine whether the minimum of the coverage given by the parents are greater than the minimum of the coverage given by the children. So minimum of the coverage of parents is 3 by 6, and minimum of the coverage given by the children is 4 by 6. So these children are better. So we'll feed it back into this generation, and then we'll continue doing this operation until we exceed the time budget. And eventually we'll increase the coverage of our test suites. So this algorithm is employed by this very popular fuzzer, which is named UOSU. Okay, so now in another approach, so fuzzers are a very good tool, but they are not the ultimate tool. So as with any tools, there could be some problems associated with the fuzzers. So one of them could be the fuzzers can stop their improvement after a certain point of time. So let's say you are crossing over and mutating your sets of inputs, and after a certain point, you see that even after multiple mutations, your coverage is no longer increasing. So then what do you do? In the traditional fuzzer approach, what will happen is that you will exceed the time budget and you will report back with whatever the best you have so far. So the question is, can you do better? So this is one approach. So this came out of Microsoft research in 2023. So the approach is called CODA-MOSA. It's called CODA-MOSA because it has two parts. The second part, MOSA, which is a fuzzer, and the first part, CODA, which is a large language model. So I assume that all of you are familiar with large language models, or at least the in which they work. For instance, I'm sure you have all used ChatGPT. So large language models are class of tools. So essentially, you can provide a query and you can try to get an answer. So by combining these two tools, the authors showed that we can try to escape these coverage plateaus with LLMs by using them in combination with fuzzers. So how does this work? So this is the traditional fuzzer. So let's say you have an initial test case population. So traditional fuzzer will start mutating test cases. You will get evolved test cases. If you will evaluate these test cases on a test program, if coverage increases, then you will update the initial population, and this will continue. Now let's take a look at what happens in this particular program. So this is a popular Python library which is called, I'm sorry. So this is a popular library which is a Python library which is called bump version. So the way bump version is used is that it is basically used to update the software versions. So if you call it with a string which looks like 0.0.0, it will give you back the output 0.0.1. If you say you can also specify a certain position 0.0.0. If you specify this position 1, then it will update the software version to say 0.1.0. And you can also specify pre-release, which is 1A, it will say 0.1.0A. So that is the bump version program. All right. So if you try to use a traditional fuzzer to try to generate test cases for this program, so you will see that, let's say you start off with this bunch of initial test cases. So the test cases, so as you see that this bump version takes as input a string, and there are optional inputs, which is this position int. So you can either give it a string or a string and a int, which will the int will specify which version to which position of the version to bump, and so on. So your initial test cases, in this case, you have generated this string, which is something garbage. And then you call bump version with this specific garbage string. And then you have a second test case where your string, the string with which you call the bump version program is none. And you have a very large integer, which you are calling this. So if you try to now execute this program with these two test cases, so you see this highlighted line of code. These basically checks whether the input that you have given to this bump version program, whether this input is invalid or not. If the input is invalid, then from this highlighted line, this bump version program will throw an exception and it will exit. So as you can see that both of these inputs, with both of these inputs, if you execute this bump version program, it will throw an exception and exit, because in the first one, this string is a garbage string. It's not formatted as per this, the way bump version expects the strings to be. And in the second case, the string that you are passing, it's none, and there is a garbage integer. It's 1431. All right. So given these two inputs, you have only been able to execute these highlighted line of code, right? So your coverage is very low. Now you try to mutate these two inputs in the hope that you will be able to improve coverage. After mutating, you will see that the garbage string still remains a garbage string. And when you increase this integer, now this 1431, after mutating, let's say you have given it a valid integer, which is 1, but your string with which you are calling it still none. So even though you have mutated, your coverage has not increased, because even with these two mutated inputs, you will still throw an exception and only execute this highlighted line. So you cannot update your population because coverage has not increased. So what do? So in this case, as I have specified earlier, you say that my coverage has stalled. Coverage stalling means after doing n iterations of the fuzzer or n mutations, you are still not able to increase coverage of the program under test. So once your coverage has stalled using fuzzers, now you can actually invoke a large language model to take a hint. So in this case, the authors used a large language model called Codex. So Codex came out of OpenAI, the guys who developed ChatGPT. It was released in 21. The interesting thing about Codex is that it's basically a code language model. So it's very exclusively trained on programs. So once coverage stalls, what you can do is that you can ask this Codex or a large language model for a hint. The hint is that you can ask Codex to say that, give me a bunch of test cases for this particular program. So Codex looks at this program and it generates these two test cases. Interestingly, as you can see that since Codex has actually looked at the source code, it produces some valid inputs. The assert statements are incorrect because Codex does not perform mathematical reasoning. So it still, it cannot execute the program. So it has called bump version with 0.0.0, and it has incorrectly inferred that the output will be 1.0.0. But at least it has produced a valid set of inputs. So the first one is 0.0.0, which is a well-formatted string for this bump version program. And in the second test case, it's a well-formatted string and a well-formatted integer. So now from these two test cases that Codex produces, you can extract these inputs and then you can try to evaluate these test cases. What you see is that your coverage increases. So now it's no longer an invalid input. So you can execute the subsequent lines of the program and increase coverage. Now you update your population of test cases with the test cases that this large language model provides. And then you can run the traditional fuzzer again. So given these valid inputs, now you can try to mutate these test cases and try to increase coverage again. So from 0.0.0, which was a valid string, you can say that the integer is -1. Try to test for more behaviors. You can say integer is -2687. Try to test for more behaviors. And similarly, you can continue. So run the fuzzer until your coverage has stalled. Once you see coverage has stalled, you can invoke an LLM to give you a hint. With the hint, you can again progress with the traditional fuzzer. So what was the improvement? The author saw that these fuzzer MOSA, if you only use this fuzzer only approach, which is MOSA, you will get 18.4% coverage on their set of benchmarks. If you only use the LLMs to generate test cases, so using the LLMs means you only take the test cases generated by LLMs and you do not do any crossover mutation operations. So using only the LLM generated test cases, you have 64.5% coverage. And if you use both of them together, you have 91.8% coverage. So one interesting thing you can notice here is that if you simply add up these two numbers, these 64.5 and 18.4%, they are still lesser than the effect that you get by using these two together. So there is a synergy between these two tools, which is a fuzzer and an LLM. So essentially, if you fuzz the inputs provided by the LLM, then you will be able to gain much more insights into the behavior of the program. Right. So this was one approach where you use LLMs in addition with fuzzers.
Sir, one question I need to ask.
Sure.
Sir, Codex only provides the test cases only. It is only responsible for producing the test cases when you provide the input, your program.
Right. It will only give you the test cases and nothing else. I mean, see,
Nothing else.
it will depend on the prompts, of course. So in this case, the authors were prompting the LLM with the source code of the program, and they were prompting that give us some test cases. So
Sir,
that's the only thing that
sir, you provide input as a source code, just a block or the complete code?
it depends. See, there are token limits associated with any LLMs. For instance, GPT 3.5 had a token limit of 4,096 tokens. And GPT-4, I think it has 8,192 tokens. So obviously, if you have a very large piece of software, you can not feed in the entire source code. So in this case, for instance, when you test, you are essentially talking about a module under test. So it's a sort of unit testing, you can say. So in this case, you can only feed the source code of the bump version program. If you want to do a system-wide testing, then like you will have to adapt your approach accordingly. So maybe you cannot give your entire source code, so you can give a summary of your functions that you are calling. So whatever comments that you have in your functions, you can provide them with the function that invokes them. Similar, like some approach like that can be appropriate.
Okay, sir. Thank you. Thank you, sir.
Sure. All right. Okay, so so far what we have looked at is how to automatically generate test cases using fuzzers, and we have seen how can we augment our fuzzers with these large language models. So now let's take a look at how to do fault localization. So fault localization, it's like I have specified before, it's a problem where you give a program, and given a program, if it has a bug, you want to identify which line of the code or which component of the code contains the bug. Now, how does the spectrum-based fault localization approach work? So to start off with, you have a test suite generator. The test suite generator takes as input a program and a fitness function. So I'll come to the definitions of this fitness function later. But essentially, this test suite generator is you can assume that it's a fuzzer. It will employ this evolutionary search guided test generation, and it will optimize the generated test suits using this fitness function. So for one example, in our earlier slides, we have seen coverage metric, right? So you can say that give me test cases where my coverage will become maximal. So that could be one of the fitness functions. Now the test suite generator, after getting this program and after having this fitness function plugged in, it will produce test suits. Now in spectrum-based fault localization, so let's first define the spectrum first. So the way a test suite will look like, it will be something like this. So remember our discussion about heat pattern. So you have a bunch of test cases. A test suite contains a bunch of test cases, let's say T1 to Tn. So each one of these rows are depicts a test case, which is a heat or miss vector, and the columns denote the components of the program. So in this case, our program has m components. By components, you can think of as m functions or m branches, and you have n test cases. And each of these cells ij, it denotes whether the ith test case executed the jth component or not. So for instance, the cell 11, it means this test case T1, it executed the C1 component, first component, but it did not execute the second component, but it was able to execute the mth component, similar to that. So essentially, after test generation, you have an 1-0 matrix. These 1-0 matrix, this is termed as an activity matrix. So once you have these activity matrix, and also you have these corresponding sets of inputs, right? Because without the sets of without the inputs, you will not have this coverage pattern. So you feed these sets of inputs and the program into a fault oracle. What the fault oracle does is that it executes the program on each of these given inputs and it produces an outcome vector or an error vector. The error vector, it will say whether the corresponding test case passed or failed. Passed or failed means it can happen that given this set of inputs, given this particular input, let's say the first input, the test case did not, the program did not produce the correct output. So that's why you say in this case error is 1. In the second test case, if you see that the program has produced the correct output, then you say that the error vector corresponding cell in the error vector is 0. It means the test case has passed. So after the fault oracle, it generates this error vector. Now you go to the fault localizer. The fault localizer takes these activity matrix and this error vector as an input. So together, this activity matrix and error vector is defined as is denoted as the spectrum of a program. So fault localizer take this spectrum, that is activity matrix and the error vector, and it assigns a suspiciousness score to each of these components of the program. After assigning the suspiciousness scores, it ranks the components in descending order based on their suspiciousness score and hands over this rank list to a developer. Now the developer is trying to debug the program, right? He is trying to identify which component of the program contains the bug. So rather than going about it blind, he can take this rank list and try to examine the component from the top of this rank list. So our fault localizer in this case has said that C4 looks like the most suspicious component. So then the developer will examine the C4 component first. Then he will examine the component CM, then C10, and so on. And the expectation is that rather than examining the program sequentially or any other order that the developer wants, if the developer examines the program in the order, program components in the order given by this rank list, then he will be able to find the bug faster. That is our expectation. Now we will see whether our expectation matches or not. So let me give you a very simple example on how spectrum-based fault localization works. So we have a very simple program. What you do in this program is that you basically get some character inputs from the terminal, and then you have three counters, which is letters, digits, and symbols. So when you encounter any letters, you are supposed to increment this letter counter by 1. If you encounter a digit, you are supposed to increment this counter by 1. And if you encounter a symbol, you are supposed to increment this counter. And eventually you will say that whatever I have inputted, it contains these many letters, these many digits, and these many symbols. Now, before going on, for the purpose of this example, we'll make two very simple assumptions. One assumption, the first assumption is that only one component in my program can be buggy. And the second assumption is that is a perfect detection. Perfect detection means if and only if a buggy component in the program is executed, then you will see a failure. Otherwise, not. Note that both of these assumptions can be violated in practice. So, of course, in real life, you can have multiple bugs in your program, and then these failing test cases can be spurious. I mean, not every time you execute a buggy component, you get a failure. That can happen in real life, and that is actually very prominent in real life. Okay, so in our example, let's say that we have 4 branches, right? So let's say these becomes our program components. So we have 4 components here: C1, C2, C3, and C4. So in C1, we will check whether this is a capital letter, and then we will try to increment the letter counter. So you see that this line has bug, right? Because when you encounter a capital letter, rather than incrementing your letter counter by 1, you are mistakenly incrementing it by 2. When it's a small letter, you correctly increment it by 1. When it's a digit, you correctly increment the digit counter by 1. Otherwise, you correctly increment the symbol counter by 1. Now, how do I detect the bug using SBFL? So let's try to exercise this program with some inputs. Let's say my first input is AB at sharp. So if I produce this input to the program, so component C2 and component C4 will be executed because you have 2 small letters and 2 symbols. And your program produces an output. It says that there are 2 letters, 0 digits, and 2 symbols, which is correct. And what is my corresponding coverage pattern? So in my test case T1, component 1 and component 3 were not executed. So these 2 cells are 0. C2 and C4 were executed. So these 2 cells are 1. And since your test case outcome is also correct, your error vector, corresponding error vector cell is also 0. So let's look at a second output, which is A13C7. Now let's see that there are 2 capital letters here. Since you hit the buggy component, which is C1, your letter counter, each time you encountered the capital letter, your letter counter incremented by 2. So now your program says that there are 4 letters, 3 digits and 0 symbols, which is wrong, right? Because you only have 2 letters. So you get another coverage pattern, which is component C1 was executed, C3 was executed, C2 and C4 were not executed, and corresponding cell in the error vector is 1. Similarly, you have a third input. So in this, your program says there are 4 letters, 0 digits, and 3 symbols. This is again wrong, and you collect the coverage pattern. The component C1 was executed because you had capital letters. C4 was executed because you had symbols. And the corresponding error vector cell is again 1. All right. So now let's forget about the program completely. Let's just look at this spectrum. So our objective is, by simply looking at this spectrum, can we somehow reason out which component of the program was faulty? So let's examine the first row of the spectrum. The first row of the spectrum says that C2, C4 were executed, C1, C2, and C3 were not executed, and the test case passed. So remember our assumption? Our assumption was that we only had a single buggy component, and a program does not fail until and unless you execute a buggy component. So given our assumption, since this was a passing test case and C2 and C4 were executed, we can infer that C2 or C4 are in fact safe components. They do not contain any bugs. Now let's look at the second test case. C1 and C3 are executed and the test is failed. So we can conclude that either C1 or C3 must contain the bug, but we do not know which one. Now let's look at the third test case. In the third test case, C1 and C4 were executed and it was a failing test case. But in our earlier examination, examining the first test case, we already knew that C4 was a safe component. Since our last test case says either C1 and C4 must be buggy, and we have already concluded that C4 was not a buggy component, then the only conclusion remains that that C1 is the actual buggy component. So by reasoning over the spectrum, we were able to catch the actual buggy component. So we can say that reasoning works, but the problem is we cannot do manual reasoning like this on a large real-life software because there could be like tens of thousands of columns here, and you can have thousands of test cases, hundreds of thousands of test cases. So there must be some automated way, right? So again, looking back to our earlier picture, you will generate the spectrum, and your fault localizer will automatically give you rankings to this component, saying that which component is most likely to be. So we had looked at the spectrum-based fault localization pipeline, which contains these multiple components, right? We had a test suite generator, we had a fault oracle, we had a fault localizer. Now, how do we measure the quality of this pipeline? So, like, what are the factors on which the quality of this fault localization pipeline lies? So the first factor is obviously the performance of this fault localization metric. So this particular component in this picture. So what the fault localization metric does is, like we had manually designed, it takes an input the spectrum, which is the activity matrix and the error vector, and it ranks the components in order of their suspiciousness. So corresponding to every column J in the activity matrix, it will produce a score Rj, corresponding to every column J. And we also have this evolutionary search-based test generator, which is we have seen before as, yes. Did anyone have a question? Okay, so I'll continue. All right. So it's a simple fuzzer. So you have a program and a fitness function, and you will employ evolution search to generate a test suite. And lastly, you have this fitness function. Fitness function is nothing but given a test suite, you quantify how good is this test suite. So given a test suite, this is a function which will produce a score S. And like we have seen before, the score can be a coverage score. It can say that what percentage of the program was covered. Now, let's look at this fault localization metric, but how do you actually compute this score? How do you compute this suspiciousness score? So for example, if you have an activity matrix and an error vector like this, and if you want to compute the suspiciousness for a component C1, you ask two questions. First question is, in what fraction of failing tests is C1 executed? So you see that there is only one single test case, and this executed C1. So the fraction is 1. And the second question is, in what fraction of tests where C1 is executed, the tests failed? So as you can see that C1 was executed twice in these test case T1 and T2, but only T1 was the failing test. So the fraction is half. And to compute the score, you multiply these two and then take a square root. So this is a very popular score, which is called a OCI score. The OCI score, using this OCI metric, you can assign suspiciousness scores to each of your components, then rank them in descending order based on their suspiciousness score and start examining components from the top. And eventually, like I have said, our expectation is that we'll be able to rank these components in order of their suspiciousness, and the buggy components will rank at the top. So the buggy component will have the highest score in an ideal situation. Ideal situation is the assumptions that we had specified, that is single bug and perfect detection. But as I have said that these assumptions do not actually hold in practice. So in real life, you will say that the buggy component does not actually sit at the top place, but it can sit somewhere close to top. So in that case, what is your quality of fault localization that you measure by wasted effort? So what is wasted effort? So once you get the rank list, the developer starts examining the components from the top one by one, right? So the components that you examine until you reach the actual buggy component in the rank list, that is the effort that the developer wastes in finding the buggy component, right? So that means the components that you let's say R was the rank of the buggy component in the rank list. So R minus 1 is the total number of components that you have wasted efforts on, and M is your total number of components. So normalizing these two, you get the wasted effort. So let's say your program had 10 components and your buggy component was ranked at number 3. So you wasted effort on 2 components. So 2 by 10, that becomes your wasted effort of fault localization. Okay, so earlier we had talked about employing evolutionary search to generate test suits, right? And we had also talked about coverage and how increasing coverage is a good goal to strive towards. So increasing coverage is definitely a good goal to strive towards if you want to know all the behaviors of the program. But is this the right metric if you want to perform fault localization? So let's try to answer this question. So here you have a test suite which has a 100% coverage, because you see that your all the like your test T1, it has executed all 4 of these components, and then T2 and T3 they also executed C1, C2, C3. So overall, using this test suite, you examined all 4 components that were present in your program. So you have 100% coverage. But if you want to perform fault localization, let's say you have an error vector which looks something like this. Now, examining the spectrum, if you want to compute your OCI score, you will see that now OCI score, it is a metric which ranges between 0 to 1, 0 being the lowest suspiciousness, 1 being the highest suspiciousness. If you examine the spectrum, you will see that OCI score for C1, C2, C3, all are 1. Now, if all are 1, if all has the same OCI score, then which component do you examine first? If C3 was the buggy component, then how do you know like these component that I want to examine first? So even though you have 100% coverage, this test suite is not good for fault localization. On the other hand, so the question is, why was the first test suite not good for fault localization, and why were all the OCI scores same? Because the way you compute the OCI scores is because you take for each component, you take the column and you take the error vector to produce your score. Now the problem is, in this case, you see for components C1, C2, and C3, all of their patterns are exactly same. All of them were executed T1, T3, and not executed in T4. So obviously they will get the same score. But if you look at this test suite, you will see that all of them has a unique pattern. So the unique pattern will guarantee that all of them will have an unique OCI score, and you will be able to appropriately rank them. So this is a good test suite. Now, how do you produce a good test suite, or how do you optimize your population of test suites to finally reach this good test suite? That is a question. So to generate test, we have this diagnosability metric. So rather than coverage metric, to generate test suites to maximize coverage, we will now try to generate test suites which maximizes diagnosability. That is your fault localization capability. So we have established that quality of fault localization, it depends on quality of test suite, and quality of the test suite can be quantified by this diagnosability metric rather than a coverage metric. Now, why do we care about this diagnosability metric? Because you can simply plug in this diagnosability metric as a fitness function inside your test suite generator, which will produce good test suites which are optimal for fault localization. Now, there are several approaches for generating test suites which are optimal for fault localization. So one of the most popular ones are called DDU. So DDU is a short form which stands for density, diversity, uniqueness. So it basically tries to optimize 3 characteristics of the activity. Yes. Does someone have a question? I'm sorry, I cannot hear you.
No, sir, please
Okay.
continue. Yes, sir.
Okay. All right. Thank you. All right. So the way DD would work is that it. Okay. So the way these diagnosability metrics would work is that they would try to assign a score to the quality of test suits, and DDU does so by examining the structure of an activity matrix. So activity matrix, you will remember, this is the binary 0-1 matrix, and the way it examines the structure is that it computes some density of the matrix, which is the number of zeros versus one, and diversity, which says that each row must be unique. Each row must have a unique pattern, which makes sense, right? Because if you have multiple test cases which produces the same pattern, they do not provide you any extra value. So they are basically redundant. So there's no reason keeping these same test cases again and again. And the third one is uniqueness. Uniqueness, as you have seen earlier, it says that all columns, or rather all component coverage patterns, they must be unique. So if they are not unique, you see that you get into this problem where the suspiciousness scores for components can become the same. So this tries to ensure these three criteria. Now, this was a very popular metric, but now our intuition was that since we are trying to optimize the fault localization score, which is this OCI score, can we directly plug in the OCI score rather than relying on this proxy, which is the structural properties of this activity matrix? So to do this, we come up with this approach, which is called multiverse analysis. So how does multiverse analysis work? Okay, so let's say we have an example activity matrix like this, right? And our question is to assign a score to these activity metrics such that it can become a fitness function and you can feed it to test generator. So rather than using coverage, you will use this particular score. Now, how do you compute this score? So to compute the score or to perform this multiverse analysis, we start imagining universes. So we imagine the first universe, and in first universe, we imagine that this first component is the B component. Now, if you imagine that this first component is the buggy component, and if you also assume that there is perfect detection meaning that you will only get a failing test case if C1 is executed, and otherwise you will not get a failing test case. So in this imaginary universe, what will be your error vector? Note that while generating test cases, you do not have access to your error vector, because while generating tests, you are not actually executing the program. You are simply generating inputs for the program. So in this case, if you imagine that this component C1 is faulty, then see your test case T1 executed this component C1. So according to your imagination, in this universe, this first test case must fail because it has executed this imaginary failure C1. Similarly, second test case also must fail because it has executed this imaginary faulty component C1. And T3 and T4, these third and fourth test cases will not fail. Now, since now you have an imaginary error vector, now you can also compute your wasted effort. So given an error vector, you can now compute the OCI score for all 6 components. And since you know that C1 is your actual buggy component, now you can see what will be your wasted effort if you try to identify C1 as the buggy component. So after some computation, you will see that your wasted effort in your imaginary universe is 3/5. Now we had in your first universe, you imagine that C1 is the faulty component. Similarly, you can keep on imagining. So if you had n components, you can keep imagining n universes where each of these components are faulty. So you imagine the second universe where C2 is faulty, third universe where C3 is faulty, and so on, up to universe where you imagine C6 to be faulty. And corresponding to each universe, you now get an wasted effort. Now, your question is, you have a set of universes. So over this multiverse, what is the wasted effort if you used your test case to identify faults? So how do you compute the wasted effort over the multiverse? It becomes the expectation over all these universes. Now note that while generating tests, you do not have any idea about which component can actually be faulty. So since you do not have any a priori information, you imagine that each component can be equally faulty. So essentially, since you have 6 components, the probability of C1 being faulty is 1/6. Same for C2, C3, etc. So now your expectation becomes an average over these over the entire multiverse, over all these 6 universes. And now this is your score. And you can plug in this, we call this the Ulysses score. You can plug in this Ulysses score as a fitness function to your test generator, which is EvoSuite. And you will be able to generate test suits which are optimal for fault localization. In fact, we had performed experiments on a set of benchmarks called Defects4j. So Defects4j are 6 real-life Java repositories, software repositories, and the programs can be quite large. I think the largest program contained something like 92,000 lines of code, and it contained, as far as I can remember, it contained 392 bugs in total over all these programs. Now, compared to the tests generated by DDU, and we compared the test suits generated by Ulysses, we see that we are actually able to decrease the wasted effort while identifying the buggy components. So in some cases, we are able to decrease the wasted effort to catch the buggy component even by 80%. Then, and if you try to examine the rank list, you see that Ulysses is able to place 34% of the buggy components within top 5, while DDU is able to do this for only 23. Similarly, if you only take the top 10 components of the rank list, 44% of the components will appear within that. So around half of the buggy components you can catch by only examining your top 10 components. So obviously this is a significant improvement, and you can actually use Ulysses to generate test suits which are optimal for diagnosability. Okay, so we had looked at these test suite generator. If you remember the spectrum-based fault localization pipeline, so there are three components, right? So you generate the test suits, then you have a fault oracle which tells you whether the test cases pass or fail, and then you have this fault localization module. Fault localization module, it will assign this suspiciousness score. So far we have only looked at the first part, which generates test suits which are optimal for diagnosability. But now we want to actually assign suspiciousness score, and we in fact want to improve quality of the suspiciousness score so that buggy component are placed more towards the top. Now, if you remember our discussion on OTI, see, it was a very simple score, right? You tried to examine like which, what fraction of test cases in which a component was executed was faulty and things like that. Now, it was a very simple metric which assumed that your program can contain only a single fault, and it assumes perfect detection. Problem is, as I have said, in real life, most of your assumptions will not hold. So in this case, what do you do? So in those cases, in real life, when your assumptions will not hold, you will still get some rankings. In some cases, they are also good, but they are not as good as we can actually make them. So to improve the quality of fault localization, that was one of our efforts. Now, why? Let's look at an example on why I say that these scores might not be as good in presence of multiple bugs. Okay, so in this case, assume that there are 4 components into our program, C1 to C4, and components C1 and C3 were buggy. whereas components C2 and C4 were not. Now, if you look at the error vector, in test cases T1 and T3, these buggy component C1 was executed. So you have these corresponding cells set to 1, saying that test cases failed. And C3 is another buggy component. So in test case T4, where the C3 component was executed, the corresponding test also failed. So now if we assign suspiciousness scores to these components, let's say OTI score. So there can be multiple scores, but let's say we are using OTI score. Then what are our expectations? Our expectations are these buggy components will receive a higher OTI score, right? But in actuality, we see that the C1 component, as expected, it receives the highest OTI score of 0.1. But C3, shockingly, it gets the lowest OTI score. So what is the reason? Reason is that the intuition behind these OTI scores is that they will tend to give a higher suspiciousness scores to those components which are involved in more failing test cases. If you look at component C2, you see that coincidentally, C2 is executed in almost all the test cases, and 3 of them were faulty. So even though C2 is not the faulty component, it still gets a high OTI score. So these components C1, there were 2 buggy components, right? C1 and C3. So C1 is essentially masking C3. C1 is the dominant fault and C3 is dormant. It is not able to get a high UTI score. So in real life, in presence of multiple bugs, what do? You try to examine these lists, you catch C1 as the buggy component, and then you go back to the program and fix C1. So if you fix C1 and you run this test suite again, what will happen? All the test cases in which C1 was executed will now pass, right? Because you have fixed C1. So after fixing C1, you see that C3 is now bubbled up to be the topmost buggy component. Now this is okay, but problem is this does not scale in practice, because every time you have to go back to your program to fix a buggy component and then rebuild your code base and then rerun your test suite, execute your program again, and then generate this spectrum. It takes a lot of time. In some cases, it might take even days to actually rebuild a code base after fixing and executing these test suites. So our idea was to somehow simulate these fix and rerank procedure. So how do you simulate these repair and rerun process? So again, we look at our multiverse analysis. So in this case, we'll use multiverse analysis for localizing multiple faults. So let's say, forget about these bottom 2 clouds. Let's say you had a original rank list where CI was your topmost buggy component and CJ was the second topmost buggy component, and so on. Now, if you had to actually do this repair and rerun process, you would go back to your program and fix CI. Now, rather than doing that, we imagine that CI is faulty, and then we imagine that we have fixed CI. So in that case, in our spectrums, like the way we have done here, we can, for simplicity's sake, for the moment, let's say we just flip these error vector bits. So if we assume that C1 is the buggy component and we have fixed C1, then we simply flip these bits. We say these tests have now passed. Once this test pass, then we will get a new rank list, like here, right? C3 bubbles up. So you get a new rank list where if you imagine CI is faulty, then you get CK and PL at the top. Similarly, you can do this from the second one. You say that you imagine CJ was the actual faulty component, you simulate the process, and CM and CN now becomes your topmost faulty component. Now you cannot do this for everyone because like it will become too large. So you assume that your dominant buggy component can only appear within the top mu ranks. So mu becomes one hyperparameter in your algorithm. Now, you need not stop at the first level. You can continue growing this multiverse tree. So in this universe, you had imagined CI is the faulty component. CK and CL came out on top. From this universe, again, you can imagine that this topmost CK is now the faulty component, and you again simulate one this repair and rerun process. Now CP and CQ becomes the topmost buggy component, and you can continue doing this for you can continue spawning universes for each of these universes again. So now this becomes your multiverse tree. So essentially, for each component CA in each of these universes, let's say you have spawned n universes, what is the score of component CA? It is proportional to a function. The function assigns a score which says that probability, like what is the probability CA is faulty given that C1 and C1 up to Cn are faulty. For instance, here you will ask the question, what is the probability CP is faulty given Ci and Ck is faulty? So once you have completed exploring your multiverse, which is bounded by multiple hyperparameters to control the size of the tree. So mu is your degree of the tree. That means how many universes can you spawn from each of your universes. Beta is the total number of universes that you can explore in the multiverse. P is the probability that a test fails after a simulated repair. So in our simple example, after fixing some component C1, we had imagined that we can simply flip the bits. But in reality, this may not hold, right? Because a test can execute multiple buggy components. So even if you had fixed one buggy component, the second one might still, or the dormant buggy component may still fail the test. So that's why after doing a simulated repair, you assume that there is a probability P with which a repair test can still fail. And S is the SBFL metric. SBFL metric means it can be an OCI metric or some other metric with which you are computing these rank lists. So once you have spawned your entire multiverse, then you can merge the rank lists from all these universes into a single rank list. The way you do that is that in each universe, each component receives a score, and in your final rank list, the score for in one component is the maximum score that a component has received in any universe. So that becomes your final rank list. And as we have seen that the final rank list is actually much better in localizing multiple faults in programs with multiple faults rather than using the simple SBFL metrics like OCI or something else. So in fact, if you look at our experimental results on these same defects4j, you will see that, so these are the simple SBFL metrics which people use, which are OCI, AD2, Barinel, etc. And if you use our tool Artemis, which is this multiverse analysis-based fault localizer, it can provide up to even 22% improvement and at least 13% improvement over the state of the art. Right. So I think I am sort of reaching the end. So I still have 15 minutes left. So let me just quickly go through another one. So we have looked at these test generations, and we have also looked at fault localizers. So let's look at a completely different ML-based approach. So again, we will look at these large language models. Large language models are very popular for their capabilities. You all know, because I think you have all used ChatGPT. So, but one very prominent problem with these large language models are that they are prone to hallucinations. So hallucinations means that they can produce outputs that may not even exist in the real world. So for example, let's say you are trying to use these some large language model to do some code completion. So in code completion, if you ask it to write code, it might call a function which this function might not even exist. You know of a very prominent example. I think we'll all know that someone had asked ChatGPT to write a paper, and it had written a very well, like it has produced a very well written paper, but all the references, all the citations that it produced were complete garbage. So all the papers that it cited, that does not actually exist. So the reason is because large language models, these are machine learning models, right? So they are essentially synthesizing their outputs. They are not reasoning over the input domain. So due to this synthesis, they might hallucinate and simply come up with these sentences which look meaningful, but they are not. So this work, it looks at, so it's called dehallucinator. So dehallucinator tries to sidestep this problem of hallucination by large language models. So one simple example. So this is a Python code from a library. So what this Python code does is that it implements a search function. So essentially, you have this data store. Data stored is a collection of documents. Let's say you have a bunch of PDF files, and you have a keyword which is a string, and you want to get back a ranked list of these documents which contains most occurrences of this keyword. So for instance, let's say you have a bunch of papers, you want to see which of these papers mention LLMs. So this function will take this set of documents and it will return this list of these papers out of all these bunch which contains this word LLM. So this is the actual code which returns the sorted list. You see that there is this relevance function which is implemented in this Python library, which is being called to find out the score of this document corresponding to this keyword. Now, if you use an LLM to try to complete this code, so essentially you are asking, so you only provide this snippet of code before the gray line, and you ask the LLM to complete the search function. And this gray line, this gray highlighted line, this is what is returned by one code LLM, which is called CodeGen. Now you see that CodeGen has produced sort of a correct output. The only problem that it calls a doc.relevance function. Now this doc.relevance function does not exist. So this is one example of this CodeGen LLM hallucinating. Another example, if you do the same thing with ChatGPT, so you will see that ChatGPT, it is invoking a function called compute relevance score with these arguments doc and keyword. So it's passing the arguments correctly. The problem is this compute relevance score, this function does not exist. So what do we do? How do we make the LLMs dehallucinate? So this paper proposes one approach, which is so essentially, before even going into this prompting business, so they have the source code of the project, and from the source code, they do some static pre-analysis. And in the pre-analysis phase, they basically index all the API calls that exist within libraries. So they are essentially extracting all the function calls and they are storing them into this database. So while invoking this LLM query, what they do is that, let's say this is your code before completion, and you are trying to ask your LLM to complete this particular code. So you send an initial prompt to this large language model. This is your completed code. Let's say you are not happy with this completed code. You say that the LLM is hallucinating. So you do an iterative query. So you know that whatever the LLM is synthesizing, it may not be correct, but it is somewhat correct. So whatever API that the LLM is trying to invoke, now you look at these store of APIs, and you try to fetch the most similar ones, and then you try to query the LLM iteratively again. Let's look at one example, which I hope will make it clear. So again, it's the same example. You are trying to complete this particular code. The LLM is mistakenly calling this doc.relevance function, which does not exist. Now, you take the completion, which is made by LLM, and you go to your API store, and you try to find out which are the API calls which are most relevant, which looks most similar to the call that the LLM has made. You will see that the call is relevance, which takes this document keyword and it returns a float, which is the similarity score. And now, rather than this first prompt, which was this initial prompt, you construct an augmented prompt. The augmented prompt contains the reference to this API. So see, you have commented this API reference, which has relevance. You have commented what this function does. And once you fire this prompt to the LLM, now you see that it is completing the code correctly, because now it has the API references available. And as you know, as someone has already asked, you cannot feed the entire source code of a software to LLMs because there is a token limit. So you sidestep that by doing this API referencing. So you store the API references and you iteratively query the LLM with augmented prompts, which results in improved accuracy. So I'll conclude my talk here. So the things that I have talked about is that how AI ML based techniques are extensively used for software development, testing, and fault localization. But there are things that I have not talked about. So these are things like these capabilities of AI and ML. So you know that I mostly talked about these testing techniques and fault localization techniques because they use AI ML based approaches. But I had not talked about these formal techniques because formal techniques are reliant on SMT solvers. You cannot go and use an LLM or any machine learning technique to say a program is correct because they are making a prediction, and your prediction does not work if you expect a proof. So essentially, if you have a machine learning model, it says that a program is correct and the machine learning model is correct 99% of times, it's still not helpful because 1% of times, as you have seen by the examples in the first slide, it can still cause major problems. But that does not mean that AI ML techniques cannot be used for verification or these symbolic execution type tasks. They can still be leveraged as heuristics. And in fact, people do use these techniques as heuristics in program verification, synthesis, and repair tasks. And in contrast, the machine learning community, they are also heavily adopting these software engineering techniques, which is these verification testing techniques, to quantify the quality of these machine learning models. For instance, you know that machine learning techniques on neural networks are often susceptible to these adversarial examples. Now, you can in fact employ a verifier to say that give me a proof that my model does not contain an adversarial examples. So, of course, this is a very difficult problem, and like this is an ongoing work, but people are attempting things like that. So with that, I'll conclude my talk. So thank you all for attending, and please let me know if there are any questions.
Thank you, sir. Is there any queries from the audience end? Okay, in chat box, nothing is there. Okay, so I hope there is no queries from that audiences. Thank you, sir, for giving us your valuable time and for your lecture. Okay, sir. Thank you from our end. Prashanjit.
Thank you. Thank you, everyone. It was
Okay.
great meeting you all.
Yeah, thank you, sir. Thank you for this speech. Yeah, for most of us, maybe this LLM and that things may be new or difficult, and that maybe the reason, but still you have explained with lot of graphs and diagrams. So somehow we get to know these things. I hope we eventually will delve more into this field. Thank you for this speech, and we would like to request for these slides because many of the
Yes.
participants are requesting for the slides.
Sure, absolutely. I'll do that. I'll send you all these slides.
Okay,
Okay. All right.
thank you, sir.
All
Thanks,
right, sir.
guys.
Thank you.
Bye.
Bye.
Thank you.
Bye.
Bye.
Bye.